Hello there and welcome back to this video series on control systems. In the past video we have seen how to draw the root locus for a simple quadratic characteristic equation. We have shown this as an example. And in the previous video we have also seen how complex numbers can be manipulated. We'll continue in that direction, and in this video we'll try to see the rules for drawing the root locus. This video may be a bit lengthy, maybe it will go up to 15 minutes or so, and it may look kind of confusing to begin with because I'm not giving any proofs as such here and merely giving the procedure. So it would be best if you note down and try to memorize it as far as possible, and try to apply these when you try to solve a problem. With that, we'll specify the outcomes of this video as you'll be able to specify the beginning and ending points of root locus, specify what do you mean by magnitude and angle criterion, what do you mean by break-in breakaway points, specify angle of arrival and departure, and points of intersection with imaginary axis. I would strongly encourage you to watch the videos 43 and 44 and take copious notes and keep them handy when you watch this video. That way you can make the most out of this video. Once again, to set the terminology we use and put it into perspective, let us consider this negative feedback system with KGS in the forward path and HS in the feedback path. You can write the transfer function from RS to CS as given here, KGS by 1 plus KGH. Okay, this we call closed loop transfer function. And this quantity that we represent here, this K multiplied by GS multiplied by HS, we call the open loop transfer function. So this KGH is open loop transfer function. This whole ratio CS by RS is what we call closed loop transfer function. Closed loop transfer function and open loop transfer function. This denominator equated to 0 is what we call characteristic equation. We are interested in the roots of this characteristic equation. In fact, when we say root locus method, we are trying to plot the roots of this equation as k is varied from 0 to infinity. The roots of this characteristic equation are important to us because Bibo stability is decided by the roots of this characteristic equation. All the roots of this characteristic equation must lie on the left hand side of the imaginary axis. Even if one root of this characteristic equation lies on the right hand side of imaginary axis, the system is no longer stable. We are trying to study how the roots of this characteristic equation move as k is increased, because we want the system to be fast. When we want the system to be fast, we need to increase the value of k. Increase the value of k, how the roots of the characteristic equation move. These roots of CE are computed from poles and zeros of open loop transfer function. So this is the characteristic equation for the closed loop transfer function, but we are plotting these roots by carefully examining and following the rules of open loop transfer function. So study open loop transfer function and plot the roots of closed loop characteristic equation. That's what we are trying to do. All the rules of plotting this root locus plot begin with the open loop transfer function, that is this KGS HS, which will be in the form given here. You have m for Mary, number of zeros, that is terms of s in the numerator, and similarly n for Nancy, number of poles. Okay, so the characteristic equation is written as 1 plus this equal to 0. You rearrange the terms and you see that it comes in this form. So and so is equal to minus k. Since s is a complex number, p1, p2, p and so on, z1, z2, z and so on are complex numbers, the magnitude of the quantity on the left hand side should be equal to magnitude on the right hand side. The angle of the quantity must be equal to the angle of the quantity in the right hand side. That is what we are going to write down. Magnitude criterion. When you take magnitude of a product, it is the product of the individual magnitude. So this product of all these terms divided by product of these terms should be equal to k. This is what we call magnitude criterion. Similarly, angle criterion says sum of angles of all these terms minus sum of angles of all these terms should be equal to angle of minus k. Angle of minus k is 180 degrees or multiple of 360 plus 180 degrees, where this q is a integer. Typically, we use this magnitude criterion to find the value of k at a point which we know ahead that it is existing on the root locus, whereas the angle criterion we use to find out whether a given point is lying on the root locus. We will show this magnitude criterion and angle criterion before we go into the rules of plotting the root locus. We consider a transfer function given over here as an example that we have already seen, and just go through the steps, noting that we are interested right now in the point s is equal to minus 1. We took this as the test point. Okay, at test point, angle s minus p1. S minus p1 is a vector going from p1 to s. P1 is here, s is here, so this is s minus p1. This whole angle is 180 degrees. S minus p2 is a vector going from p2 to s, so this angle is 0. So angle s minus p1 plus s minus p2 is 180 degrees. Because it is 180 degrees, this point is lying on root locus, which we clearly see. At this point, if you want to find what is the gain k, you apply the magnitude criterion, that is s minus p1 into s minus p2 is 1. K is equal to 1. Similarly, if you take the same example and consider the trial point at some other place, some other point in S plane. Let us say we take the trial point to be something like this, 3 plus 3j, 3 plus 3j as shown over here. So angle s minus p1 is 3 plus 3j minus 0, s minus p2 is 3 plus 3j plus 2. Angle of s minus p1 is tan inverse 3 by 3, and angle s minus p2 is 3 by 5. If you sum them up, you see that it is not equal to 180 degrees or 180 plus any multiple of 360. So this point is not lying on root locus as is shown here. With that, we'll begin with the rules. As I mentioned, I'm not going to go into the proofs of these, and I'll give you just overline of these rules and how we apply them, and then we will see a couple of examples. So I'd request you to be patient and note down the details. We know the beginning point is k is equal to 0 and the ending point is k is equal to infinity. So k is equal to 0 gives the beginning point, is equal to infinity gives the ending points. So k is equal to 0 means all this is equal to 0, because we have written all this is equal to minus k. Okay, k is equal to 0 means the poles. So at each one of the poles you have one branch of root locus beginning. Similarly, at each branch, at each 0, one branch terminates. So there are n number of beginnings, m number of endings. So the difference n minus m is the number of asymptotes that along which the root locus plot goes to infinity. This rule 2 kind of breaks the whole plot of root locus into two whole regions. One region existing on the real axis, the other region away from real axis. So we'll see as part of rule 2 where this root locus exists only on the real axis. To decide in which regions on real axis you have root locus existing, the others do not matter. That is this P5, P6, Z4, Z6, they do not matter. We are only concerned with poles and zeros lying on the real axis. The rule we follow is root locus exists at a point on the real axis if the sum of number of poles and zeros to the right of that point is odd. For example, you consider a point shown here, somewhere here. Okay, if this were to be the point, you count how many poles and zeros are there on the real axis towards the right hand side. There is only one pole which is odd. So root locus exists at this point. That is, we can say this point is actually the root of characteristic equation. Whatever applies to this point also applies to this point, also applies to this point, also applies to this point, and every point in between P1 and Z1. So we draw the branch thickly here, from here to here. All here roots exist. Then if you consider a point here, the number of poles and number of zeros, if you sum them up, you have one here and one here, 2. It is not odd. So the roots do not exist between these. And then root exists between these. And then roots do not exist. And then roots exist. And then roots do not exist, and so on alternatively. I think you get the idea. All this region, no roots. Here you have roots. Here no roots. And again roots. Again no roots. Again roots, no roots, and so on. We have seen that if there are n number of poles and m number of zeros, there are n minus m asymptotes. We are going to state here without proof that all these asymptotes meet at a point on the negative real axis, and we can compute the angles that these asymptotes make. Those are the things that we are going to show on this. The point where they intersect, where the asymptotes intersect, is given by the sigma, sum of poles minus sum of zeros divided by n minus 1, and the angles are given by this. You vary q from 1 to n minus 1 and substitute here, and you get the angles. We'll see this with an example and it will become clear. And then there are places on real axis where the root locus move away from real axis. That is, for some time the roots are real and then suddenly they start becoming complex. That point is what we call break away point or break in point when reverse happens. And this you can find by differentiating this transfer function and equate it to 0. There may be several roots of this, and we select the one that is appropriate. We'll see what is appropriate later, and reject the others. The next important thing is angle of arrival. I would strongly recommend you to remember this rule. This comes from angle criterion, sum of all the poles other than the pole we considered. For example, you are trying to find at P sub k what is the angle of departure at p sub k. Sum all this pk minus pi, pk minus p1, pk minus p2 and so on. Similarly pk minus z1, pk minus z2 and so on. But for pk itself you substitute pk. So just remember this. From this you will evaluate what is the angle of departure. Similarly angle of arrival you find from this. And the only other aspect that is remaining is points of intersection with imaginary axis. We write the characteristic equation. We build routes array for this characteristic equation, and the points of intersection appear as the roots of auxiliary polynomial. That is, you will have a row of zeros. Right above the row of zeros you have auxiliary polynomial, and these roots of this auxiliary polynomial give us the points of intersection. Once you apply all the 6 rules in situations where they are applicable, for example, in some situations rule 6 need not be applied, or in some situations rule 3 need not be applied, and so on. With that, we will summarize by saying that root locus plot allows us to draw the roots of characteristic equation, observing the poles and zeros of open loop transfer function. So from open loop transfer function to the roots of characteristic equation, that is what we are going to see. And by the method given by Evans, you can find out all these beginning and ending points, where are the roots lying on the real axis, break in, break away, and then centroid, asymptotes, angle of arrival, departure. All these things you can find out. We'll try to see a couple of examples and try to explain these. I think that's all we have for now. Have a great day.